Okay, so today we're going to look at some theory. We're trying to understand the logic behind how probabilities are determined in the binomial option pricing model based on the Black-Scholes framework. Okay, so remember, all the assumptions of this binomial option pricing model are the same as those of the Black-Scholes model. That way, both of them in principle should provide the same prices for European options. If they didn't, that would be a cause for concern because it means that we couldn't have any confidence in the American option prices that it produced. But because we can show that at least if we have enough time steps, the binomial option pricing model gives us the same results as the Black-Scholes model. That's how we know that we're implementing the Black-Scholes model correctly, and that we can then turn around and provide consistent prices for American style options. Anyway, now what we're about to do is actually what the Black-Scholes model is doing as well. In other words, what we're really doing in this model is we're not really directly pricing options. What we're doing instead is creating what's called a replicating portfolio. Okay, let me mention this here somewhere. All right, here we go. Okay, so the Black-Scholes and the Cox-Ross-Rubinstein binomial option pricing model are based on the logic that if a portfolio could be created whose cash flows are guaranteed to match those of an option at all points in time, then the market price of the option must match the market price of this portfolio. So there's what we're saying is, listen, if we could create a portfolio whose cash flows are always the same as an option, then what we will find out, of course, is that the market prices have to be the same because otherwise there'll be an arbitrage. Okay, so if you notice as we go along, the logic behind a lot of what we're doing is based on this notion of arbitrage. And so if not, if the market prices of the portfolio, which we will, by the way, call replicating portfolio, and the option, then arbitrage territories. Okay, so in other words, how would that work? For example, if the replicating portfolio is cheaper than the option, then investors would buy it. And I'm sure we've talked about arbitrage enough so that you can see right away that you're buying whatever's too cheap and selling whatever's too expensive. So you would buy replicating portfolio and sell or take a short position the call. Okay, so in other words, sorry, this could be a call or a put. Now, in this case, with stocks, short selling is a very tricky thing to do. There's a lot of restrictions on it. With options, anybody can sell an option, even when you don't already own. Okay, so in other words, you can write an option or sell an option to somebody else. What it means is you're taking a short position, and that means that whatever cash flows belong to the owner of the option are coming out of your pocket. So it's easy to set up a short position in an option. Not so easy with many other financial assets, but with derivatives, it's easy to take a short position. You might remember, for example, that with a forward contract, you can take or create a short position by agreeing to sell something in the future. Same thing is true with a futures contract. You're basically taking the position where you're selling something in the future, and you benefit from declines in the price of the asset. So here, you're buying the portfolio and short selling the option or selling the option. Now, what does that accomplish? Well, for one thing, you're clearly putting money in your pocket today. Okay. If you're selling something that is cheap and buying, sorry, if you're selling something that's expensive and buying something that's cheap, then clearly there's a difference there that it goes into your pocket. So the investor would collect the difference between the prices today. Okay, fine. So money goes in your pocket now. Now in the future, since the cash flows of the replicating portfolio and the option are guaranteed. Remember, we assume that they're guaranteed to be equal at all points in the future. The long replicating portfolio, or what I should say is the cash flows to the long position in the replicating portfolio will exactly offset those of the short. I guess we'll continue on the next slide. Oh no, here we go. Okay, in other words, a dollar income from one would lead to an outflow to the other of a dollar. In other words, it would be like, I guess, borrowing $100 and then repaying $100. The two exactly offset each other. So no matter what happens in the future, the income that comes in from my long position is paid out to whoever has the short position. And so that means that in the future, there will be no net cash flows. Okay. And of course, this will continue until the option expires, which it will eventually. So in other words, so you've got a scenario where this means that the investor collects a positive cash flow today and has no net cash flows in the future. Okay, so in other words, this is a risk-free or arbitrage. This should not happen in an efficient market. If it does, arbitrage will cause the underpriced asset, which in this case is the replicating portfolio, to increase in price, while the overpriced asset to decrease in price until they're equal to each other again. Because that's the only time when there's no arbitrage opportunities. So this process will continue until the two equal each other again. So in other words, in the process of exploiting this arbitrage, we are forcing the prices back together. And so they will quickly, this will quickly be eliminated, this opportunity. And I think I mentioned this before, that there are hedge funds called statistical arbitrage funds, where all they do is have computers look through real market data in real time with very, very powerful computers, and they look for these temporary discrepancies between markets, and they the computer that is, jumps in and buys whatever's undervalued and sells whatever's overvalued. And so a lot of these opportunities disappear so quickly that human beings can't even take advantage of them, because by the time they notice, it's already gone. So the computers are doing all the trading, and they're looking for the opportunities. So they're programmed to look for these opportunities that could, even in a very efficient market, arise for very short periods of time, meaning fractions of a second. And so because all these computers out there are looking for these opportunities, it means either they'll never arise in the first place, or if they do, they'll disappear so quickly that it will be too fast for human beings to even notice it. Okay, so yeah, it is like it used to be 40, 50, 60 years ago, an investment bank could have a team of what they were called arbitrageurs, people whose only job was to look into market prices and see if there's any opportunities. But of course, in those days, trades were made over telephones. You didn't have computers, or at least not very fast ones. So not everybody had the same information at the same time like they do now. So it was much easier for arbitrage opportunities to rise than now. So, but the important detail here is that the reverse is also true, by the way, before I continue. If the replicating portfolio is more expensive, then you would just do the opposite. Okay. So if the portfolio is more expensive than the option, then you would just do the opposite. So they would sell the replicating portfolio and buy or take a long position in the option. Of course, you'd have the same outcome. That's kind of awkward. Buy or take, I should say, take a long position in the option. Okay. And then, of course, the same thing would happen. In other words, now the portfolio, because it's overvalued, the price would fall. And then because the option is undervalued, the price would rise. And very quickly, the two would equal each other. Okay, so the prices would converge to each other very quickly. So again, you rarely see this in the real world anymore, or at least not for periods of time that are observable by human beings. Not that it's impossible, but it's so unusual. It would mean that somebody made a terrible mistake, or somebody's computers weren't working that day, or something had to be wrong. So what this indicates then is that for all practical purposes, you can count on the price at any given point in time. Price of the replicating portfolio and the price of the option will be at the same. Okay, now there's LVI identical. So what does this have to do with anything? Well, that being the case, the Black-Scholes model actually reprices the replicating portfolio and uses it as a proxy for the option price. So they're saying, well, listen, if we know that they have to be the same at all points in time, then why not just price the replicating portfolio, and that will give us our option price. So in other words, the Black-Scholes model doesn't really, technically doesn't price options. It prices the so-called replicating portfolio. Oh my God. Well, that's pretty interesting. So and that's because, by the way, the replicating portfolio consists of assets whose prices are well known. They're very easy to find in other words, they trade very frequently. So it's easy to get a hold of market data for these assets in the market portfolio, replicating portfolio. And so therefore it is easy to price. Now, options are different. Options don't trade nearly as often as, let's say, stocks. Okay. In fact, an entire day can go by, and some options may not trade at all, or just a few times. So options are not nearly as liquid as the underlying assets that they're based on in most cases. So market prices can be a little tricky. Okay. You figure, well, they trade all the time, right? No, it's stocks, yes. Currencies, yes. Not options. They do trade, but not nearly as often. So the fact that we can price an option based on the replicating portfolio is actually a huge deal, because like I said, the assets in that portfolio are much more liquid than the option itself. So, with all that being said, what we're going to do now is understand what this replicating portfolio is all about. Now, we're going to do this based on the binomial framework, but it applies to the Black-Scholes model too. Okay, the difference between the two is that The binomial framework basically assumes that time is elapsing at discrete time steps, like a day at a time or a month at a time, whereas the Black-Scholes model is assuming that time passes continuously, but in the limit, as the time steps in the binomial model get smaller, the two models will converge to the same results. Okay. So you can think of the Black-Scholes model as the limit of the binomial option pricing model, where there's essentially an unlimited number of time steps. So here we go. Now this is it. Now remember, we decided to use the letter F to represent options in a Holzbook because, if we use P for puts, they can easily be confused with probabilities. So Hull decided that F stands for both calls and puts. So if you can see here, we're assuming now, of course, remember in the Black-Scholes model, it was designed to price options on non-dividend paying stocks. So that's what this discussion is based on. For something else, where there's some kind of cash flow, we would have to modify this discussion a little bit. But this is the original Black-Scholes model. So it's written on some common stock. And so the replicating portfolio consists of only two things: shares of the stock and treasury bonds. Okay, that's it. Now, this matters a great deal because the treasury bonds are considered to be risk-free. That means all we need is a combination of these two, and we have a portfolio whose cash flows will exactly match the option. Now, it's a lot more complicated than it sounds, because the trick to the whole thing is how many shares of stock we need to hold and how many dollars worth of the treasuries we need. And those two numbers need to be updated at every time step. Otherwise, the two would never match each other. Okay, so that is really the challenge. The number of shares and the number of dollars worth of bonds. And by the way, these treasuries that we're looking at, it will be understood that their maturity matches that of the option. So in other words, if it's a 6-month option, then we're using 6-month treasury bills. Okay. And then of course the stock itself. So the H is chosen, we use the letter H because it's called a hedge ratio. Okay. And the portfolio is a replicating portfolio, since the whole purpose of it is to make sure its cash flows match that of the option. Here, we're starting our discussion with the call option. Okay. Now, here's what we're going to see. Now, again, we're assuming we're in the binomial framework. And so I'd like to remind you that in this framework, stock was assumed to go from S to SU and down here to SD if it goes down. And since the portfolio consists of H shares of the stock and B dollars worth of bonds, then what we can do is draw another graph showing the value of the replicating portfolio. Okay, in fact, I'll do that right here. So in other words, if this is our S, SU, SD, that's our delta T. Remember, delta T is the time between steps, and that is expressed as a fraction of a year. Well, when we start doing this on VBA, we'll usually assume this is something like a quarter of a year or half a year, and then we'll see how to change that. Okay, and you'll also see that as we keep shrinking up the delta T, the accuracy of the model will improve. All right, so the corresponding tree for the portfolio is going to look like this. We start with H shares of stock and B dollars worth of the bond, whatever it is. What happens to it in the future? Okay. Actually, fix this graph just a little bit. Now, here's what I want to point out, though, before we go any further, just as a quick reminder. That this is a risk-free security. The Treasury bill we're looking at. Okay, its future now value is known with certainty. Because the cash flow is guaranteed. Okay, so remember, future value refers to value of an investment that is invested at a specified rate of interest for a given time period. So in other words, we're looking one period ahead. And remember, R is the risk-free rate of interest. So, and one more thing too, don't forget too that Hull is assuming continuous compounding. So with continuous compounding, the future value of a sum of money is going to look like this, or at least a risk-free sum of money. Okay, so let's say I'll use the letter. I have to be careful here not to be confusing. Let's say that the current value of this sum is A. Okay. And then one period later, this becomes A e to the R delta T. Okay, so the E is there because this is a continuously compounded rate of interest. The R is the risk-free rate of interest that applies over that period. And delta T is the time step, the size of the time step. And the fact, now, by the way, if this was not a risk-free investment, then R would have to be different. It would have to reflect the actual risk of this investment. But since we're assuming that this is risk-free, then that means its future value. Oh, I forgot to write. This is future value. Must be that amount times e to the R delta T power. Okay. So you think of it as this is the guaranteed amount you'll have in delta T time steps. And let's say delta T is a year. That means in 1 year, our investment will be worth AE to the R times 1, actually, or just R. So the same thing is happening here with our replicating portfolio. We have these treasury securities whose value is known today, whose future value is guaranteed. So when we draw the little tree, I'm going to move these down here. We know two things. The stock in the upstate is worth SU, so we have HSU here. And then the bonds are worth the future value. Okay, so in other words, we know that the stock is worth SU, which we multiply times H because that's a constant. It's the number of shares that we own. The B is guaranteed to be worth BE to the R delta T. It doesn't matter whether we go up or down. So that means down here we have HSD plus B, again, BE to the R delta T. And again, one more time, the distance between the two time steps is delta T. Okay, so the way we're going to do this is assume that this is a call. We know that in one time step, if it's a 1 period call, the value will be equal to the payoff in one time step. All right, so here's what we're going to do. Now, in general, just if we're not moving to the terminal nodes here, we can simply write this as FU and FT. Okay. All right, so we really can think of this as being three trees, I suppose. There's the stock, there's the option, and then the replicating portfolio tree, as we just saw, is going to be either HSU plus BE to the R delta T or HSD plus BE to the R delta T. So that's what it says here. In other words, they're setting these equal to each other. Because by assumption, the cash flows have to be the same. And of course, in turn, knowing that the future cash flows are equal means that today, the price of the option today must equal the value of this portfolio today. So again, what we still have to be careful about here is that we still don't know the values of H and B. Okay, so in other words, what we're going to do is look for the values of H and B that guarantees that all of this is true. Or we can prove that this is a risk-free cash portfolio, or at least the cash flows are guaranteed because to be equal to the option. So now there's going to be a lot of messy algebra. So what I did is I went ahead and actually did it for you. This is the result. These, by the way, are simultaneous equations. And so you can use any technique you want to solve for H and for B because those are the variables that we're interested in. I'll save you all the gruesome details. Okay. I know you know how to solve simultaneous equations. So if you do that, this is what you'll ultimately end up with. So that's our hedge ratio. Okay. This is the number of dollars worth of the treasury security that we buy. Okay. Now you can see these values we know. Okay. We know U, we know D, because when we set up the tree, to be consistent with the Black-Scholes assumptions, remember we define U to be E to the sigma radical delta T, and D is this, the inverse. Okay, now, by the way, these are not the only possible choices they could have made. Cox-Ross and Rubenstein, as far as they were concerned, they were just trying to show how the Black-Scholes models work. They didn't claim that this is necessarily the best approach, but they wanted it to be intuitively easy to follow what they were doing. And later researchers did come along and, they have different variations of this tree, but they still must follow the Black-Scholes model. Okay. And so if we used a different value of U and D, we'd have different calculations for H and B as well. Okay. So this is what we have. And now you're probably wondering, well, what happens if we substitute some of these values in here? So, like I said before, assuming that the cash flows are the same in the maturity date, that implies that the prices are equal today. And that's where we get this. Now, again, I'm saving you a lot of messy algebra, but if you took these two definitions and plugged them in here and did a lot of algebra, this is what you'd ultimately end up with. And so you can see, it's kind of interesting because this term means present value. So remember we had that diagram before. A rose to AE to the R delta T. If this is a risk-free investment, we can flip this around. Say, well, listen, what if it's the other way around? What if I want to know the present value of A? If A is being received in the future, it means this would be AE to the minus R delta T, because these two are inverses of each other. So this term would be known as the present value of A. And so that's the significance here. This e to the minus R delta T on the outside means that whatever we're doing here, we're calculating the present value. So inside the parentheses, what you're seeing is a bunch of terms. And I'll just give you a hint as to what's coming. This term is what we're going to call P, and this is 1 minus P. This is the risk neutral probability of an upward movement and this would, of course, have to be the risk neutral probability of a downward movement. Okay, well, I just barely fit it in there. Now, why are these the correct values? Well, because, I mean, again, you can prove it algebraically if you want to. It's a bit of a mess, but you can do it. It's not that difficult, but it'll take a while. What we want to do, though, is prove that these do, in fact, have the correct properties to qualify as probabilities, by which we mean that they must be between 0 and 1, and they must add up to 1. Okay, so in other words, in order for these to qualify as probabilities or be interpreted that way, we need to know two things. Number one, these two individually are bounded between 0 and 1. And number two, they have to add up to 1. Now, it's not immediately obvious that these are both correct. But Cox, Russell, Rubenstein's model is based on some key assumptions. Among them are the values of these terms and how they're related to each other, which I know they're in here somewhere, but I want to go find them just to show you. This is now when they suddenly become important, these assumptions. Here they are. We're guaranteed. The G, remember, is the real world probability that we don't actually need. Let me grab these. You'll see why this is so important. Because it'll help us demonstrate that these terms do have the correct properties. All right, so based on these assumptions, that what happened? Oh, wait a minute. Oh, there they are. There they are. Okay. I just messed it up. This comes up here. And so that will help us understand why this one, by the way, is P. Let me just repeat that again here. This is P and this is 1 minus P. So how do you know that this first one is, in fact, between 0 and 1? Well, because by assumption, e to the r delta t is greater than d. So this is positive, but u is assumed to be greater than r delta t, which implies, in turn, that u minus d is less than, greater than rather, In other words, the numerator is smaller than the denominator, and yet the numerator is positive. Okay, so the numerator, actually, let me write it like this because this is the denominator. The denominator is greater than the numerator, and the numerator, r delta t minus d, is guaranteed to be strictly positive. Okay, because of this right here. And that's what we needed to prove for p. You know that it's less than 1, although it could technically be equal to 1, and the numerator is guaranteed to be positive. And so based on the same reasoning, the same thing is true down here. And so we're guaranteed that these are probabilities because they're guaranteed to be between 0 and 1. And in addition, algebraically, we can demonstrate that these two do add up to 1. If you look carefully at this, you'll see they have a common denominator, which is nice. The r e to the r delta t's cancel out, and we're simply left with 1. Okay, so in other words, yes, we can interpret these as probabilities. Now, they're not real world probabilities. They're what we call risk neutral probabilities. And let me show you what that means. They're consistent with a return to an asset equal to, I have an example of it in a minute here somewhere, to an asset that equals the risk-free rate of interest. So they're consistent with a return to an asset that equals the risk-free rate of interest. So we have to be able to show that if we had some asset or other. Oh, all right. Well, let me just show you graphically, and we'll do the algebra in a second. Let's say we have some asset. I don't know. Let's try A again. It must be true that the price of A today is the present value of what we call the expected value of the future cash flows. Actually, I should call it the expected future value, because you see what we're doing here. You remember from stats, the expected value of X is simply, let's say we have X times, well, actually, let's make up an example real fast. So let's say we have some random variable X, the probability of X being 1 is a half and -1 is a half. Expected value of X, this would be like a coin flip where you get a dollar for heads and you lose $1 for tails. On average, if you play this game, coin flipping game, the expected value, meaning the weighted average of these probabilities, or actually the weighted value of the x's where the probabilities of the weights is equal to 1 times a half plus -1 times a half, which is 0. And so that's what you're seeing here in these parentheses or brackets, I should say, is the expected value of this a asset in one time period. And since that expectation occurs one period in the future, the value today must be discounted back to today by the risk-free rate of interest because it's guaranteed, it's risk-free. So this is the structure we'll use throughout this chapter. The cash flows to an option have a value equal to the present value of their expected future cash flows, where we're discounting the cash flows with a risk-free rate of interest and using risk-neutral probabilities. Okay, so the two have to be consistent with each other. If we were using a different assumption besides risk neutrality, we'd have a different set of probabilities, but we would also have a different rate of interest that is consistent with that risk. All right, so in other words, if this was a risky security, the P's would be different. The R would be a little higher because you'd have to use a higher discount or interest rate. So here we're going to demonstrate why these probabilities lead to a risk neutral result, because again, with S, SU, ST, T equals 0, T equals 1, the times difference is ST. Now, this is meant to represent the expected stock price or delta T in the future. Okay. And again, what we're doing is, since there's only two possible outcomes, P means we've gone up, 1 minus P means we go down. So if we go up, we go to SU. If we go down, we go to SD. So what we're going to do is substitute those two definitions I just showed you, and let's see what happens. Okay, so in other words, the P is replaced by this expression, and the 1 minus P is replaced by this expression. And you'll be surprised, well, maybe not, that when you go through all the algebra, wow, you end up with the future value of S, where the rate of return is the risk-free rate of return. And that's what we mean by risk neutrality. So there's those P's are the only probabilities that are consistent with a risk neutral framework, meaning that the returns are equal to the risk-free rate of interest. No matter what happens, our average return will always be the risk-free rate of return with these probabilities. Okay, so in other words, what Hull and White were, Black and Scholes were able to prove is that this framework results in risk-neutral prices. Okay, these prices that they are generating are guaranteed to be consistent with risk neutrality. Wow. Now, in the Black-Scholes model, though, let's go back to that for a second. What they had to do, though, is show how H and B evolve over time, consistent with market conditions, so that the replicating portfolio was always going to give us the same cash flows as the option. That's where all the math got involved. They needed to specify these very complex equations to specify the behavior of H and B. But the point of it is that at every given point in time, H and B have to be the right values to ensure that the replicating portfolio matches the cash flows to the option. So here in the binomial option pricing model, we're basically using that background to do the same thing. Okay, so this is what you need to remember right here. This is all the results look just like this one. In other words, at time today, time 0, here's our F. It goes up to FU or F down to FD. But its value today is the present value of the expected value delta T in the future. Now, the reason why we have to do this is because we don't know what it actually will be. Okay, we're not trying to forecast or foretell the future. What we're saying here is that we know what on average it should be. Okay, sometimes it'll go up, sometimes it'll go down. What is it going to be equal to on average? And that's what this is telling me. All right, now, and you notice what's missing from all this is G, the real world probability of going up or down. It makes no difference. We don't need it. Okay. So you're thinking, well, how is that possible? Because the way the framework is set up, risk preferences do not affect the final result. And that's what the beauty of this is that all the results are based on observable market variables. We don't have to deal with figuring out what people expect to happen in the future. We don't have to deal with their risk preferences. We can just assume everyone's risk neutral. They're willing to accept the risk-free rate of return on their investments. That's it. That's all we need. By the way, this is you can see that the Black-Scholes model is introducing a lot of these extremely important ideas, like this concept of risk neutrality. Nobody had done this before. This is their idea. Now all derivatives models are based on the concept of risk neutrality, risk neutral probabilities, the idea that the prices are arbitrage-free prices. This is all they're doing. Okay, so they're path breakers, right? And in fact, they blazed many different trails with their paper. All right, so let's see, what is our first example here? Oh, I'll tell you, I'd like to see some graphs here. So yeah, if we have a one period model, this is how we're going to price it. A one period option, that is. Okay, now I'm assuming that this is a call. And and it's a one period model, which means that this is the maturity date of the option. And that implies that the option's value in this time step is equal to the payoff. Oh, by the way, I mentioned this. We have to be careful here. Some parts of the slides here, I'm using a K. Sometimes it's an X. That's because I started out. I was one of the first buyers of Hull's book. I had the first edition at one point, one of the very early editions, and I seem to remember somewhere along the way he switched from X to K, and I've never recovered since then. So just remember the X or K can mean the strike price. Okay. So all right. So remember, in general, the payoff to a call option is just max S minus K and 0. So here, though, in the upstate, the stock price looks like this, and in the downstate, it looks like this. So that means we only have to calculate F at one node to come up with the price of the option. So it's going to look like this. Present value and then remember, we're looking at the expected value of the option in one time step. So we need P times FU. That's 1 minus P FD. Okay, there's a P, or the probability of going up is P, of going down is 1 minus P. If it goes up, the value is FU. If it goes down, it's FD. Now, if you want, you can plug these into here to come up with the exact numbers. But other than that, you're all set. And in this framework, Coxhorse and Rubenstein were able to prove that the P's have these formulas that we just looked at. So Other than that, you're done. It's very straightforward. Okay, so soon enough, we'll start writing VBA code again. And when we do, our first example will be one of these. We're just going to understand how to set this thing up so you can calculate the price of an option in one or possibly two time steps. Now, if we go past a single time step, it gets a little messier. For example, let's see. So it can either go up to SU or down to SD. And then we have another time step. From SU, it can go up to SU squared or down to SUD. These are the same by assumption. And this is SD squared. Let me clean that up a little. But you get the idea. All we did here, and of course, these are implied. So if you go up twice in a row, it's SUU or SU squared. If you go up and then down, it's SUD. Down and then up, it's the same thing by assumption. And then down and down is SD squared. So that means our tree for options is a little messier. What do you have to take into account here? All right. Well, the maturity date is easy. Because remember, whatever the maturity date is, the option will always have a value equal to its own payoff. So here that would be max SU squared minus K0, max SUD minus K0, and max SD squared minus K0. So we now have three interior nodes, and each one will use the same logic that we just saw. FU will be the present value of the two nodes that we can reach. We just barely squeezed that one in there. And then this one, hold on. There we go. All right. So in other words, the present value, always the present value, and then P means we're going up to this node. 1 minus P means we're going down to this node. And then finally, F itself is going to be this. Because from F, we can only reach two nodes, FU and FD. Now, what you can do here, if you want to come up with an expression to solve this directly, you can replace FU and FD in this formula at the bottom here. And if you do that, in other words, you substitute, you'll end up with this. So first, we're looking 2 periods ahead. So the discount rate will be actually minus 2 R delta T. And then we'll have this. So that would be a somewhat more compact way of writing this. So in other words, if you did directly substitute FU down here and FD down here, That's what you'd end up with. Okay. Now, one of the advantages of doing it this way is that you can write a program that where you can set it up so that you can program it to solve F no matter how many steps there are, all with one formula. But it gets a little unwieldy, and it might be easier when you're starting out to do it one step at a time, but just be aware that it can be done. Okay. So somewhere in here, there's an example. Now, by the way, if we're dealing with an American option, that changes our results because, so in other words, up to this point, it's all been based on European options because, and this is what we'll have to save until next time. FU and FD and E are and at these two nodes, I should say, there's at least a chance you might want to think about exercising the option early because it's a 2-period option. We have the right to exercise it in time step 1 if it makes sense. That means with an American option, this part is fine. We have to make a decision. We have to compare each of these results with the price of the option if exercised, and that will help us decide if we should exercise or not at each of these nodes. So there's at least a chance of early exercise at all the interior nodes. And so we have to make decisions as we go along. Do we or do we not exercise this option early? Okay, this diagram is for the European one where there's no decisions to be made. But once we start allowing for that, it does get a little messier. Okay, so anyway, I think it might be a good idea to save that for next time. All right, and so I'll see you then.